every time Earth goes around the backside between the sun and Jupiter, Jupiter's going to tug on it a little bit. Comes back around again, Jupiter tugs on it again. Jupiter has a strong gravity. What's going to ultimately happen to Earth's orbit? In this scenario, Earth's orbit will become more and more elongated. The gravitational tug of war between the sun and Jupiter will yank Earth out of its orbit, destabilizing the solar system. Not only Earth, the other planets as well. He said, oh my gosh, this will take time, but clearly the solar system is stable. So he writes, can't understand why it's stable because I know my equations work. So God must step in every now and then to fix things.
So why hasn't Jupiter's repeated pull slowly torn Earth from a safe, nearly circular path? The counterintuitive starting point is that gravity in our solar system is mostly conservative, which means it trades energy and momentum back and forth without creating a one-way drift unless the timing lines up just right. An orbit is a repeating path set by a balance between a body's inertia and gravitational pull. In a pure two-body system, energy and angular momentum are exactly conserved, producing stable ellipses. Our foundational assumptions are that the sun dominates the gravity, there's no drag in space to dissipate energy, and the planets are far from colliding. Under these conditions, Jupiter's occasional tugs on Earth can speed Earth up during some alignments and slow it during others. Because the direction of the push relative to Earth's motion changes around the orbit, those pushes largely cancel over many cycles, unless their timing is coherent. The immediate insight is that repeated push does not imply accumulating push in a conservative system. A second insight is that without a mechanism to keep the pushes in phase, you mostly get fluctuations that average out rather than a sustained drift. What makes a small gravitational push accumulate rather than cancel? The answer is resonance, which is when two repeating motions line up with a simple timing ratio so that the same part of one cycle meets the same part of the other cycle over and over. A mean motion resonance is a locking of orbital periods, like two orbits returning to the same relative positions every few laps. This alignment keeps kicks in phase so their effects add. Phase coherence means the relative angle of the bodies at each meeting is repeated, maintaining the direction of the push. The foundational point is that only coherent timing converts small periodic forces into a steady change. Otherwise, the sign of the kicks alternates and sums to almost zero. In our case, Earth and Jupiter are not in a strong mean motion resonance, although their periods sit near 12.1 commensurability. That high-order resonance is weak and not locked, so successive alignments drift and the geometry of each encounter changes. Additionally, the orbit's precess, meaning the orientation of each ellipse, slowly rotates in space, further scrambling the alignment. The key insight is that resonance is the pathway for accumulation. Without it, conservative forces mostly cancel in the long run. A second insight is that precession acts like a phase randomizer that breaks any nascent buildup. Why are Earth and Jupiter not trapped in a dangerous resonance? Planetary systems are not arbitrary. They are the survivors of early violent evolution where unstable configurations were removed. During formation, planets likely migrated through gas and scattered off leftover planetesimals, processes that can both create and destroy resonant locks. Dynamical selection means that configurations prone to close encounters or strong resonances tended to self-destruct, leaving behind arrangements that avoided the worst overlaps. This is supported by numerical models of early solar system evolution. Observationally, the asteroid belt contains wide Kirkwood gaps where resonances with Jupiter destabilize asteroids, demonstrating that resonances are real and destructive when present. The lack of such a resonance near Earth's orbit is direct evidence we sit far from strong commensurabilities. Exoplanet surveys also show that some systems end up in resonance chains, while many do not. This diversity indicates that both capture and escape from resonance are common, and survivors are biased toward long-term stability. The synthesis is that our current architecture is not accidental. It is a filtered outcome where large resonances between terrestrial planets and Jupiter do not persist. The second takeaway is that space between planets is not just distance. It is separation in the space of frequencies, which matters more for stability. Even without mean motion resonance, can slower, cumulative effects still grow Earth's eccentricity? Yes, through secular interactions, which are long-term exchanges that act on the shapes and tilts of orbits rather than their periods. Eccentricity is a measure of how stretched an orbit is. Precession is the slow rotation of an orbit's long axis. A secular resonance occurs when the precession rate of one orbit matches a mode of the system, allowing gradual alignment of the directions of orbit elongation and a steady transfer of eccentricity. The solar system's secular behavior can be approximated by adding up contributions from each planet. Jupiter provides the dominant terms that force Earth's eccentricity, with Saturn and the other planets contributing additional modes. Their combined influence produces bounded, quasi-periodic variations, most prominently the remarkably stable 405,000-year cycle, rather than a monotonic growth. Two additional detuners help. General relativity adds a small extra prograde precession that shifts the frequency slightly, and coupling with the other terrestrial planets, especially Venus and Mars, sets Earth's natural apsidal precession away from exact matches with the dominant Jovian mode. These statements are theoretically established and confirmed by precision modeling. For Mercury, the relativistic precession is known to offset a stronger secular interaction that would otherwise be more chaotic. The immediate insight is that slow drifts are real, but frequency mismatches prevent them from piling up indefinitely. A second insight is that multiple small effects, mode coupling among the terrestrial planets and relativistic precession, act as stabilizing offsets by spoiling exact frequency matches. If the planetary problem is known to be chaotic, why doesn't chaos guarantee eventual ejection? Chaos means sensitive dependence on initial conditions, where tiny differences grow over time. A Lyapunov time is the characteristic E-folding time over which tiny differences grow by a factor of E. In a conservative, weakly perturbed system, chaos does not necessarily imply unbounded motion. Many trajectories remain confined by surrounding regular regions. The Kolmogorov-Arnold-Moser result, in plain terms, says that when perturbations are not too strong, a large set of quasi-periodic motion survives indefinitely, creating barriers that confine wandering. For Earth, the absence of close encounters with giant planets keeps perturbations weak, and numerical integrations show its semi-major axis varies by minuscule amounts over billions of years. This is computationally established with independent long-term simulations. By contrast, Mercury sits closer to secular resonances and shows a small but non-zero chance of large eccentricity growth on multi-billion-year timescales. The key insight is that chaos can be bounded. You can have unpredictability in phase without a runaway in energy. A second insight is that avoided close encounters are decisive. Dramatic energy exchanges require proximity, which our current spacing prevents. What, then, is the precise reason Earth's orbit remains stable despite Jupiter's repeated tugs? The stability is a layered outcome. Conservative forces make uncoordinated kicks cancel. Strong mean-motion resonances that could coordinate those kicks are absent. Secular interactions exist, but are detuned by the combined influence of Saturn, the other terrestrial planets, and relativistic precession, and any residual chaos is bounded because close encounters are avoided and the system retains many confining, quasi-periodic motions. Practically, ejection would require energy transfers comparable to Earth's binding to the Sun, and without resonance or encounters, there's no pathway to accumulate that much energy. Historically, the early solar system likely removed architectures that lacked these protections, leaving a configuration that, while not perfectly predictable in detail, is robust in its overall shape. So, Jupiter's tugs are real, but their timing does not lock in, their long-term averages cancel, and the remaining fluctuations are corralled by frequency mismatches and conservative constraints. That is why Earth is still here. Like if this was interesting, and hit the subscribe for more.